Hi, I'm Ben-Yaakov. This presentation is entitled Simulating a Physical Inductor by LTspice. The problem that I'm addressing in this presentation is simulation of an inductor. Here I'm showing just a simple inductor here, assumed to be at this stage without a gap, and the ferrite has some BH curve, which is of course nonlinear, and the purpose is to develop a model that will take into account the nonlinearity of the ferrite when running a simulation by LTspice. Now, LTspice has a feature which is very convenient here, and that is you can describe an inductor by the flux equation. X is the current, so you can write an equation flux is equal to a function of this current. It could be nonlinear. Actually, it could be also a table. In the example that I'll give, it'll be a function. And then you can run it, and it'll take, of course, into account the actual behavior according to this equation. So this is a very nice feature of LTspice. I'm talking about an average BH curve without considering at this stage the hysteresis. And I'm going to show step by step how to develop this function and how to find all the parameters that are needed in order to fit the behavior of the model to a physical inductor which has some dimension, has a BH curve to the ferrite, and with or without a gap. A very convenient function that I'm going to use in this presentation is the tangent hyperbolic function, which behave very similar to the BH curve that we are familiar with in a ferromagnetic material. And this is why it's really very handy to use, and I'm going to use it in this presentation. But the method I'm going to show is by no means dependent on this particular function. This is just an example. Let me just make a side note here that it is important to remember that BH curves are highly temperature dependent. So if we build the model according to a specific BH curve, then we have to realize that this will be, strictly speaking, accurate for one temperature. Another temperature, the BH curve is changing. So let's have a look at this tangent hyperbolic function. It looks like that, sort of it saturates here, and here it's just about a straight line. It's a little bit curved. I'm just approximating it as a straight line. And the function we are talking about, this is flux. Actually, it's n times the flux, which is defined as the flux. And this is the template we are talking about. It's a constant times the tangent hyperbolic function, and there is another constant here, and this is the actual current. So we have a function of n phi as a function of I. This is the definition needed for LTspice to run the simulation. Okay? Now the tangent hyperbolic function by itself at 0, when x is 0, when this is 0 here, then it is this point here, the 0 point. And then for large x's, much larger than 1, then the value is 1. Okay, so it sort of saturates at 1. Now this slope, which you can define as the derivative of n times phi with respect to I, then this is actually inductance, because inductance is n phi over I. So this is the local inductance here, and I'm assuming that throughout here just about a straight line. So therefore this derivative here is in fact the local inductance of the inductor at this range. Obviously here it's changing. So what is the derivative of this function? It turns out to be this value, that's k1 then, times k2, and then the derivative of tangent hyperbolic, which is 1 minus this value. And this will be at the initial point, which I assume to be 0, so this is actually 0. So therefore this slope here is k1, k2. meaning that this is K1 times K2 is actually the inductance. Okay, so this is the inductance. Now in a typical BH curve, we have the maximum magnetic flux density where it saturates, and then this will be equal to this n phi, which is the function we are working with, divided by n first of all, and then by a. And since when this function is 1, that is for large value, n times phi is k1, then this ratio here is k1, this is the n phi at large values, divided by n, because we have an extra n here, and then divided by a to get from phi, from the flux density as we want it here. So therefore from here and here I can define k1 as n times a b max. And then there's another point we can choose, and that is when this function is 1. When this function is 1, then we have a tangent hyperbolic 1, and as it turns out, when tangent hyperbolic is 1, we get to 0.76 of the maximum. Okay? So, using this information, and knowing that I is h LE over n, Ampere law, then putting the value for h, this is the h here, as k2 times hk, LE over n, and this is from here, and this should be equal to 1, from which I can get k2, and then knowing k1 and k2, and knowing that k1 times k2 is indeed the inductance at this region, I find that when plugging this value and this value into k1 times k2, I'm getting this equation, which is of course identical to the famous or known equation for the inductance of an inductor, n squared a, b max over h is mu, total mu, and then we have the magnetic path length. So everything seems to be coming into order. We have the value of k1, we have the value of k2, and then we have checked that indeed k1 times k2 is indeed this inductance as we expected at the beginning. Now we're coming to an example, and I've taken an example, a toroid, which is of these dimensions, and I've chosen this particular material, the ferromagnetic material, which has a 10,000 mu I, that is the initial permeability, this is this slope here, and then it has a AL of 5,500 nanohenry per turn, or 5.5 microhenry per turn. And then it has this LE, magnetic path length, and AE, the magnetic cross-section area. Now, for HK, that is the point where the function tangent hyperbolic is 1, we have here 40 amp per meter for about 0.76 of the B max. So this is another value that we can get from this curve, as well as B max to be 430 millitesla. So we have everything. So now we can calculate K1 from this expression, which comes to be 34.6 10 to the minus 6. I've chosen 10 turns. The inductance according to the data sheet. This is the data sheet, and this is the AL value. So therefore, the inductance for 10 turns is 10 squared over 100, which is 550 microhenry. This is just the value from the data sheet. Now K2 is also given, so I can calculate it, and it comes up to be 14.4. Actually, it's 1 over amp, but let's leave alone the units here. So K1 over K2 from this calculation here, using this equation that I found earlier, it comes to be 500, while according to the datasheet it should be 550. Again, There is some nonlinearity here, and the initial value of the AL is of course for one particular point here, so I think it's a pretty good match. Let me just point out that in some cases, in some BH curves, this is not really very flat, it goes up a little bit, so there is another section here which is a function of the current, and if you'd like to take into account, you can just add another term here, and you can find this slope from the BH curve from the datasheet. I'm not doing it here, just mentioning that you can do that if you wish. So let's see now how it works. This is the inductor, and it is defined by this equation, and these are the two constants that I found earlier from the particular inductor that we are examining. I've now added a couple of more things here. Number one, I have added a dependent source which is equivalent to this expression. So by solving it, I can find n times phi, because this equation is supposed to show n times phi. And then I've added another dependent voltage source here, which is the derivative of this n phi with respect to the current, and therefore this is actually the inductance. Okay, so this will be the inductance at any given point. Now, to be able to take this derivative, which is with respect to time, I have made this source, this current, defined by time. So 1 second means 1 amp, 2 seconds 2 amp, etc. So by this, I can take this derivative with respect to time, which is also the derivative with respect to the current. Okay, so this allows me to do that. And here is what I am getting. We see the n phi is going up. This is the Tangens hyperbolic function. It sort of levels off at 34.5, which is the constant of this function, very close here. And here I have also the inductance starting at 500 as we expected. By the L I'm getting 550 as we've seen before. So this is pretty good. Now this value is 34.5 microvolt, but this is n times phi. So I can convert it to B by dividing it by n and A. And here is what I am getting, 450 millitesla, which is very, very close to what we have seen in the datasheet for the BH curve. So it seems that this model here works very nice. Now, what about the case we have a gap? If we have a gap, the BH curve is really modified, and this is now the slope here is the equivalent permeability rather than the initial permeability of the ferrite. Bmax is the same. So what really happens here, you might say that at this point at which the argument of the Tangens hyperbolic function is 1, this point is moving from here to here. Now it is moving by the same ratio as the permeabilities. Okay? So we know what is the permeability of the ferrite. We know what is the permeability of the body we have. Well, I'm not going to go over it. There are some videos in my YouTube channel which discuss it thoroughly. So we know what is the permeability of this body. So we can now move or get another value, a modified value for this point here. So now K2, this value here, has to be modified by this value here. And as an example, if we are considering the initial permeability, which was 10,000, and then if we assume a permeability for the gapped core of 100, the ratio is 100, and by plugging it into the equation for the Tangens hyperbolic, running it, here is what I am getting. So now let's compare the two. This is with the gap, and this is without the gap. Now here we have 500, should be microhenry inductance. Now since the gap now reduces the permeability by a factor of 100, now the inductance is 5 microhenry, which is okay. But N times phi for this core is the same because it has to do with B max. So here we got 34.6, say, and this is pretty much the same. So we can see that you can actually run both a gapped or ungapped core without any problem. The key here, of course, is to find K1 and K2. So what we need is the cross-section area, magnetic path length B max, and this point HK from the BH curve, or the gapped case when this point moves. We can calculate K1 and K2, and then we can plug it into this function for the flux, and here we go. We have a nice representation of the BH curve, and therefore we can run a simulation of this nonlinear case. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.